Gordan's work from the paper that he will be telling us about today. Gordan is at Fermilab and has appointments at the University of Chicago, including the Kavli Institute for Cosmological Physicists. He's a particle physicist working on, at least one thing I know he's working on is efforts to detect dark matter, novel experiments for doing so. Anyway, I was delighted that Gordan was able to, on Friday, decide to give this talk on Monday. And anyway, I'm very much looking forward to this. So thank you for being virtually here, Gordan.
No, thanks for the kind introduction. And today I'll tell you about a fun thing that we're recently working on, inspired by one of your recent papers, Lloyd. It's dark atoms and their connection to the Hubble tension. It's mostly a model building project with some pros and cons, and I hope we'll get through that as the time goes on. But this is based on a very recent paper with Nikita Blinov and Shirley Lee. And I'll start off by telling you a story in 3 parts. I'll review a few about the Hubble tension, which I imagine everybody here is already quite familiar with. I'll set it up by talking a little more about dark atoms and cosmological perturbations and what we would like to gain by introducing them to the universe. And then I'll get to the real point of our paper, which is what it would take to build a realistic model of this that satisfies all the requirements that we would need to provide a good solution to the Hubble tension. So without further ado, to get everybody on the same page, you've probably seen lots of tables like this. This is from a recent paper by Di Valentino et al. And this is giving a nice summary of all the measurements that people have thrown at the present day Hubble constant. In fact, I think it's already a little bit out of date. We've already seen a few more added to this list, but the general state of affairs is on this slide right here, and that you can see that almost all of the early universe measurements of H0 tend to cluster towards the left pink band, and all of the later universe stuff involving supernovae and Cepheids and several other techniques tend to cluster to the right, giving a number roughly about 74 kilometers per second per megaparsec, whereas the Planck and early universe measurements tend to give numbers closer to about 68 or so in those same units. This has now been a long-standing discrepancy. And of course, there are a few measurements like tip of the red giant branch, which tend to straddle both of those numbers with slightly larger error bars. But generally speaking, the early measurements that we have are indirect. They assume some cosmological model. And then based on that cosmological model, taking a snapshot of the CMB, you can then forward project what H0 ought to be given what you observe in your CMB data sets. So this is a model dependent measurement of H0. And then, of course, we have late time measurements, which are really just getting at the expansion rate of the universe today, getting distance redshift relation, calibrating it appropriately using a variety of techniques. And these, of course, get the larger value of H0, at least on average they do. And it wouldn't be doing my due diligence without acknowledging that there could very well be an unknown systematic in at least one type of measurement, though to my knowledge, no one has found a plausible candidate for what this could be in any of these data sets. And it might also be evidence of new physics in cosmological observables, since of course the tension is between a model dependent extraction of a quantity and a much more direct model independent way of measuring it in the later universe. And so that's perhaps an opportunity, a clue that we're missing something in how we think about the early universe. And the way that we would infer the Hubble constant from CMB and BAO observables is by using 2 distance scales that in turn determine an angle that we measure. So we measure the angular diameter distance to the surface of last scattering. And this is a quantity that depends on the distance to the surface of last scattering, and it also depends on the distance that a sound wave had time to propagate towards in the very early universe up until the surface of last scattering. This is a quantity that depends on the integrated Hubble rate at early times. And so if you modify early universe cosmology in a suitable way, you can change how we would extract that, because ultimately what we measure is theta sub s. And it's much harder to modify late time cosmology and changing the angular diameter distance to the surface of last scattering. And so perhaps the most promising way of changing the relationship between H0 and CMB data is by doing something around the time of matter radiation equality, for example. And there's no shortage of attempts that people have thrown at the wall trying to make this happen. And so here from a recent review of BSM solutions, this paper I think was entitled The H0 Olympics, trying to give medals or distribute shame, depending on your opinion of these things, across the variety of different models that people have written down. And one thing that you can see right off the bat is that without going into any details about what these models are, the thing that should really sort of strike your eye in this slide is that the tension that you get, even after you've added new physics, tends to be pretty significant. Even if you've done something weird, like adding a bunch of dark radiation and interacting dark matter and dark radiation, you've maybe added curvature, early dark energy, you've varied the electron mass, you've made dark matter be kind of warm, but maybe not, you've made some of it decay, you've added a primordial B field, you've done all these great things. And at the end of the day, you might have a tension that's still about 3 sigma, which is not great. And you've done quite a lot to change the composition of the early universe, going well beyond the standard model. And if you'll notice that almost everything here provides a pretty poor fit, except for maybe 1 or 2 things that, depending on how they chose to quantify the resulting tension after adding these new ingredients, still only gets you to about 2 sigma tension in the best case scenario. And the ones that really tend to do the best have, in my subjective opinion, some of the weirdest ingredients, where you're simultaneously adding some amount of curvature to the early universe and you're varying the electron mass. And that still gets you to about 2 sigma tension. Nothing really lands you right in the middle of where you want to be. And so I think it's fair to say that there's strong motivation for any model that agrees with CMB data better than anything that we see up here on the current slide, that it's generically hard to be compatible with the CMB data set itself. And so with that in mind, I'll say a few words about dark atoms and what they might help us achieve in taming some of these effects on cosmological perturbations that imprint themselves on the CMB data set. So, oops, went a little too far. So when we talk about cosmological perturbations, what we generally do is we perturb around a flat isotropic and homogeneous background of FRW type. And we define 2 principal quantities for each fluid that we care about that's present in the early universe. So delta is the density contrast, dimensionless quantity, how much you deviate from the average density point by point. And there's the velocity divergence, which is just a proxy for the velocity field of each fluid, also as a function of space and time. And then you open up your Birch-Singer and Ma, and you look at what the linearized Boltzmann equations are for each fluid in the early universe. And then the solutions to your Boltzmann equations, as you propagate them forward in time, at the snapshot of the last scattering surface, give you something that you can convert into the plot that we're seeing here. This is a plot of the CMB temperature power spectrum. And the solutions to this Boltzmann system ultimately determine your CMB anisotropies. They're sensitive to the composition and the interactions of the fluids that are present at early times. Now, it was interesting to learn from Lloyd and friends recently that there's an interesting symmetry or approximate symmetry that this system has. that might be useful in taming some of these theoretical problems and trying to enhance the Hubble rate. So it turns out that under certain assumptions, namely that you're working in the regime of linear cosmology and recombination is instantaneous, that your Boltzmann solutions are invariant under a set of rescaling transformation. So here we can just, for now, think of F as a constant. And so if you take everything that has the dimensionality of a rate, so Hubble and any quantity that scales as root g rho, or a number density times a cross section, you rescale all of those by an appropriate constant, the same constant. And you also suitably rescale your initial spectrum of primordial perturbations. This will preserve the solutions to your Boltzmann equations at linear order. And that is sufficient to guarantee that you have a good fit to CMB observables. So the moral here is that if there's any kind of attempt at adding new stuff to the early universe, if that can be shoehorned into essentially mimicking the form of this scaling symmetry, then that'll automatically be protected, or at least much better protected against doing violence to the CMB data set relative to what earlier attempts have tried to fling at the wall here. So this is potentially a very interesting step in the right direction if we can find an appropriate set of fields and interactions that'll do this for us. The only problem with doing this, though, of course, the one that sort of hits you in the face right away, is that we're constrained in how much rescaling we can do based on the fact that at least one of these fluids is known to exquisite precision. Namely, we know the present day CMB temperature quite well, to part in several thousand. And that means we can't just willy-nilly rescale the photon density. That would affect what we've already observed. And also, even if we wanted to be agnostic about, say, the photon temperature, rescaling the quantity that gives us the electron-photon scattering rate is not quite as easy to do, because there you need to either change well-measured standard model parameters, maybe like the electron mass. This is potentially one of the reasons why this is something that shows up in some of these solutions. Or you have to change the history of recombination such that you can adjust the rates accordingly. And that's not allowed unless you're willing to give yourself considerable freedom to deviate from the standard model. Well, okay, but we can't change standard model physics, but we can at least approximate the effect of performing this rescaling by adding a subdominant hidden sector. In this talk, I'll refer to this hidden sector as standard model prime. So for the time being, let's just imagine that every time that you see a primed variable from here on out, it refers to some quantity that lives in a hidden sector that doesn't interact with our standard model fields. And so at face value, this has all the right ingredients for what you might want. We now have a standard model and a standard model prime that are present in the early universe. And if we perform the rescalings in an appropriate way, we maintain that the ratios of energy density fluids are consistent across the board, that we ensure we just have the right amount of each kind of fluid to maintain the same ratios that we have in our sector, then doing a binomial expansion here gives us an approximate representation of what we might want our F to be. This at least works for the rates that go like root g rho. And we have to satisfy a certain set of conditions right off the bat. So first and foremost, the hidden sector has to be colder. So whatever temperature you have off in that other sector better be smaller than our temperature. That's pretty intuitive. We don't want that to massively overclose the universe. We don't want it to be an enormous deviation away from existing cosmological measurements. We need the density ratios of fluids to be roughly equal in both sectors. And we need to make sure that recombination happens at the same time, because the growth of perturbations is sensitive to when recombination happens. And so if it were to happen at different times in the two sectors, that would introduce an opportunity for the benefits of this scaling relationship to no longer be realized, at least after a certain point. So these are roughly the ingredients that we want to realize. And this actually turns out to do quite a great job. So from Lloyd and friends, here we're looking at two plots that tell us what fraction of atomic dark matter relative to the dark matter density. So not a total fraction of the early universe, but just a fraction of the dark matter, which is, I guess, sort of similar at these times. We can get a much larger value of H naught that agrees quite well with CMB observables. And we do so with a few to maybe 5% fraction of atomic dark matter relative to the total. And the rest of the dark matter can be something else. It can be axions, it can be your favorite cold dark matter, it can be a WIMP. And similarly, we want the temperature of this hidden sector to be somewhere between maybe 0.5 and 0.7. And choosing those as best fit parameters tends to satisfy the requirements that we want to realize. So that's great news. The main problem with this is helium. And so the other cosmological observable of interest here is the helium mass fraction. So this is something that shows up in a variety of different contexts. We measure how much helium there is in the late universe. It's about 0.24 relative to the total baryonic mass density. And this is also a number that we could in principle treat as a free parameter in terms of how we perform our calculation of BBN yields. So how many light elements do you get from Big Bang nucleosynthesis? And the value that provides us with good agreement between theory and observation is consistently this 0.24, 0.25 number. And it turns out that that's one problematic thing about this construction, that since we're able to rescale or we're at least able to mimic the rescaling of all the energy densities in the universe, and we can make H naught larger, that plays along with the kind of rescaling that we'd like to realize. It's much harder to rescale how electrons scatter off of photons, because that's ultimately imprinted into diffusion length scales in the CMB data set. So while we're able to rescale H and root G rho, the issue we run into is with silk damping, because the electron number density is sensitive to the helium fraction. And so in order to get a good fit to CMB observables, what was done in this earlier paper is that YP was allowed to float. And so if we go back to the earlier slide, what we'll notice is that the observed value here is along this vertical pink band. Oh, and there's a question. You should feel free to just speak up and interrupt me, please.
Hi, I was just wondering what the shaded regions, the colors correspond to. I'm not sure if you explained it already. Like, what's this red shade region versus the blue one?
So I'm sure Lloyd would be a better person to ask for this, but my understanding is that these were different assumptions made in how the scans were performed. So one of these models did a brute force rescaling, take some choice of F and then rescale everything, and that gave a certain set of ellipses. Then there was another which added just dark atoms but didn't do anything else except allow for YP to float. And the one that corresponds most straightforwardly to just adding dark atoms is the interior blue ellipsoid, the one that stretches least far out and is perhaps in greatest tension with YP. But maybe Lloyd can say something a little more about that if I didn't get it quite right.
Yeah, close. And so the first thing we were just putting the scaling in by hand. So it's just a one parameter extension. Those are the green curves, the open contours. Those and the data that's that Faye, who's also here and could explain this, he made the plot. The data used there is Planck and BAO data. That's in all of these. And then the blue and the red both differ by just letting, instead of enforcing the scaling, letting the densities of these dark sector components, the dark neutrinos, the dark atoms, the dark photons, letting those all vary freely. And so that broadens things up because there's more freedom there. So you get the red, and the difference between the red and the blue is that the data for the blue you now include the Resetal data, right? So that's why the blue is in that that band favored by Riesedel, the measurement of the Hubble constant.
Mm-hmm. Thanks. Yeah.
Thank you.
So that actually sets us up quite nicely for the remainder, because for what I'll discuss throughout the remainder of the talk will be motivated by trying to realize models that live in the blue. But before we get there, just a comment on the helium fraction, that since adding a hidden sector doesn't automatically address issues with regard to modified silt damping in the CMB data set, modifying YP tends to move it more in the direction of performing that rescaling, to my understanding. And so that's why the FIT seems to prefer that if we allow it to float. So this is a generic issue, and it'll be an issue that everything that I'll tell you about will inherit. And we'll see how that goes. But beyond the helium issue, there are just a few things that perhaps might strike us as troubling about just adding dark atoms and requiring all of these other things. So for example, we need the hidden sector to be colder, which is perhaps straightforward. It shouldn't be too hard to make sure that whatever mechanism after inflation populated both of those didn't quite put them at the same temperature. That's not so weird. But then, the energy densities that we get are sensitive to temperatures, and we need equal density ratios of each component fluid in each sector. And we need recombination to happen at roughly the same time in both cases. And of course, on top of that, depending on how complete of a story you want to tell, you would also need a mechanism to generate the baryon asymmetries in both sectors, which in turn might be related to how you set the temperature ratio. And so it would be nice if there were a complete story that just made all of these things happen without a great deal of work or without any kind of extraordinary coincidence. And
I have a question.
Yeah.
Can I go to the previous slide?
Yep.
Not the comment. Because this seems very fine-tuned, but let's assume I impose the initial condition, all the initial condition, like the requirements, 3 requirements. Then what's the condition similar to some parameter in your model? For example, fine-tune in the case, if you vary your model by 1%, then you got result huge difference. But I'm just saying, I just set the initial condition. Do I get a similar fine-tuning in the sense is very similar to some parameter in your model? That's my question.
So what I mean by fine-tuning in this sense is that if you don't, if you were to just throw darts in the parameter space, you say I have a standard model sector and a mirror sector, and then I just let the temperatures start off perhaps at some arbitrary value, or maybe even you fix the temperatures to the value that you want. Yeah. You still need to make sure that, say, the energy density ratios work out to be the same. And that's a function of how much of an asymmetry you have. So you would still have to explain, say, I mean, if that's the place where you want to start the clock, then sure, but we know that there's a mechanism in our sector that gave us, say, what the baryon density was in relation to the temperature of the photons, for example. And so the question is, if you were to then try to tell a parallel story in a hidden sector, how much of a delicate tuning would you need in order to make sure that everything worked out properly if you wanted to tell the whole story? So I hope that that part will become clearer as we go forward.
Okay.
But did I address at least the spirit of your question?
Yes.
Okay, great. But feel free to bug me about this later if what I'll tell you ultimately doesn't satisfy you. But one place that I do want to focus on is recombination, because it's something that's very sensitive to the ratio of the binding energy of hydrogen to the temperature of the photons. It goes as alpha squared and the reduced mass of the electron proton system and the photon temperature at the time of recombination. And of course, alpha is set by the electron charge. It's set by the standard model Lagrangian, by QED. The electron mass is set by the physics of the Higgs sector and a vacuum expectation value of the Higgs itself and a Decay coupling. The proton mass is set by the QCD confinement scale. And the temperature in principle is just set by some initial condition, set by whatever populated the universe with radiation. And so, if you look at this, you're really drawing from ingredients that involve lots of very different aspects of fundamental physics. And I would think you would need quite an extraordinary coincidence for the ratio of binding energy to temperature to be the same in both sectors, which is what would guarantee that you had recombination take place at the same time. And so for the rest of the talk, I'll try to convince you that there's a realistic way of realizing at least the model building ingredients that get us to the place where we'd like to be. So I'll say right off the bat that what we're not going to do is solve the helium problem, which is unfortunate, and I wish I could tell you otherwise. So if that's a disappointment, I'll understand, and you're free to leave. But I will say quite a bit about the coincidence and potential fine-tuning issues and what it takes to tell the complete story, going all the way back to baryogenesis and so on, and reheating. And so our setup is going to be at face value the same kind of construction. We're going to have a standard model and a prime standard model. We're primarily going to be concerned with protons, neutrons, electrons, photons, and neutrinos. These are the main fluids that influence CMB observables, and we're going to want to make sure that they're added in the right proportions with the right properties to give us what we'd like. And if you're familiar with the literature on twin Higgs models, we're going to want both sectors to essentially have the same properties. And here I'm thinking of mirror twin Higgs, if that's familiar to you, where in an effort to solve the hierarchy problem, you have a mirror sector of the standard model itself, same couplings, but different Higgs vacuum expectation value. Now in twin Higgs models, you generally are motivated by the hierarchy problem, and so you'll want the hidden sectors VEV to be larger than our sectors VEV by some order 1 amount. In this story, which is perverse from the perspective of twin Higgs, we're going to want the opposite. We're never going to thermalize these sectors. We're just going to imagine, sort of like with either twin Higgs or n naturalness, let's say, that we've got multiple copies of the standard model, and the dynamics of how the universe is populated and reheated will preferentially populate some sectors relative to others in a way that's dictated by the value of the Higgs VEV in each. And one consequence of setting up the story in this way is that the fundamental fermions will have different masses in the hidden sector. Those will scale linearly with the VEV. But since all the couplings are the same, and that means that the strong coupling constant is the same, and all the same UV boundary conditions apply in the hidden sector, that means that lambda QCD, the scale of hadronization, is going to be the same in both, up to very small logarithmic corrections that will depend on the VEV ratio. And so what's funny is that we'll have different electron masses, but we'll have by and large the same proton mass. And this will be important later on. Yep.
Can you give us a sense of like how close do you want lambda QCD to be? Like what's the ratio of m electron prime over m electron versus lambda QCD prime over lambda QCD?
So the formula for how lambda QCD changes as a function of Higgs VEV is known. I don't know it off the top of my head, but I know that it's log sensitive to the...
yeah, I'm just asking you what numbers you want for phenomenon.
For lambda QCD, let's say sub% level, and that's automatically realized. For the electron masses, we're going to want some order 1 ratio.
Yeah, I'm not sure that would be automatic, because actually the heavy quarks, especially the charm quark, contributes a lot to lambda QCD. So if you're changing that by a factor, you're going to change the lambda QCD by at least something like 20%.
I think that even if it were 20%, I don't think that would be a problem, because ultimately what we want to do is live in these ellipsoids. And the timing, I mean, so the proton mass primarily enters in as a reduced mass. And so the reduced mass is going to be dominated by the electron's mass anyway. So I'm not particularly worried about that, but we did check this, and we can fish out the formula later on. When we put the numbers in for what we needed for the VEV ratio, it ended up being about a % level correction to my memory, but maybe we can revisit that.
Okay.
So what we would like to do is generate the asymmetries in both sectors using a mechanism inspired by Affleck-Dine baryogenesis. And so before we dive into how that works in our story, I just want to review it very broadly in its generic form. So Affleck-Dine baryogenesis consists of introducing a baryon-charged scalar field. It's a complex scalar, and it has our honest-to-God B minus L number. It could be baryon number or just B minus L number. So something sort of like a squark. And this was originally conceived in the context of supersymmetric models in the 80s, but nothing about it specifically requires supersymmetry. And I'm not going to refer to supersymmetry any further, except as a historical note here. So imagine you have some action of this particular form. There's some complex scalar with baryon number, and its potential is going to involve terms that both preserve and violate baryon number. So anything here, the first two terms, for example, that goes like phi star phi, is going to go like the norm, and there's no phase sensitivity, and so those numbers will preserve baryon number, whereas terms that go like, say, phi to the fourth without the norm, or phi star to the fourth, are going to constitute explicit breakings. And so if you have both of these realized in your setup, that helps you satisfy some of your Sakharov conditions. And the final ingredient that we need is a B minus L preserving decay interaction with standard model fields. And so the way that this works cosmologically is well, before we get to the cosmological part, let me just say a few words about writing this in polar coordinates. So it's helpful to imagine that phi is r e to the I theta. So its potential now explicitly has terms that go like the radius only, and then terms that have some sort of phase dependence in the cos4 theta piece. You can use the usual Noether current to figure out what the baryon density is that's stored in this field. And you can see that it depends on the radial part, and it also depends on the time evolution of the phase. And the nice thing about this is it has an integrable equation of motion, which should actually remind us of orbital mechanics. This is really a 2D problem, that you have some radial and angular terms that are evolving in time. And what you would notice is that if the right-hand side were 0, in other words, if baryon number were preserved, then the only thing that could influence the evolution of baryon number is Hubble expansion. And that's ultimately what the left-hand side encodes, that if you were to set the right-hand side to 0 and then solve that by integration, you would find that the baryon number would have to scale as a to the minus 3. But because we have this angular dependence, that means that there's a way to actually add net baryon number, so that even if you started with 0, this is sort of like an equation that tells you about conservation of angular momentum in orbital mechanics, but in the presence of a torque, which means that you can add angular momentum. In this analogy, of course, baryon number is angular momentum. And now for the cosmological side of things, we imagine that the field is displaced from its minimum at early times. And this is very early times after inflation, but before the baryon asymmetry has been introduced. The field could dominate the energy density of the universe, although that's not a strict requirement, but we do need it to be displaced from its minimum, which is not particularly hard to do if it's lighter than the Hubble rate at inflation. And so it ends up generically at some place in the complex plane. And so even if you started with a 0 baryon number, you would quickly find, due to this torque from the explicit baryon violation and its potential, that you would end up with a non-zero value at some later time. And so as long as the phi field decays through baryon preserving interactions into standard model particles, they then inherit the baryon number that was built up through this mechanism. And so unlike a lot of other baryogenesis mechanisms or leptogenesis mechanisms where you have to fight back reactions and you have to fight washout, and you're really trying to make a lot of use of interference between tree and loop processes, here you almost have the opposite problem. You almost get too much of a baryon asymmetry. This, to my knowledge, is the most efficient way of pumping extra baryons into the universe. So it's nice to just work with that, because you can get a big number if you like. And what we're going to do is we're going to generalize this to having two sectors. So we're going to have one field phi. It's going to be exactly like what I just told you. But now we're going to add the additional lever, which is that we're going to give it different branching fractions to the primed and unprimed sectors. For reasons that will become clear, I hope, going forward, the main thing that we're going to want to require is that the branching fractions to each sector, or that the widths to each sector, are going to scale as the VEV of each sector's Higgs to the 4th power. That seems like a funny requirement, but we'll get to why we need that. And aside from this, everything else about Affleck-Dine baryogenesis is the same. We just now have to just keep track of how much of this net asymmetry stored in this field phi gets communicated to the two sectors. So it's exactly the same idea, but with a slight twist. And we're going to want, in order to ensure that the branching fraction has the scaling that we want, to choose a decay operator that lets this field phi couple to Higgs squared in each sector, so that when you square the width, you'll get a VEV to the 4th dependence. We're going to demand that everything else in the theory is the same. So whatever operator you choose to transfer the asymmetry in our sector will have the same form in the other sector with the same prefactor, except for the Higgs VEV. And here we're imagining this is just some higher dimension operator, and we'll say a few words later about what form that should take on if you'd like. But if we now imagine that the scalar dominates the early universe, it's just some matter-dominated era, where this field is doing its dance in the complex plane. This is a low-temperature early universe. We haven't added radiation yet. Phi is dominating. It sets the clock, and then it starts decaying, and it decays now in such a way that the ratio of branching fractions to the different sectors now scale as the ratio of EVs to the 4th power. And the logic here is that these decays will reheat both sectors. If the energy density that each sector gets scales as VEV to the 4th, then the energy density, which determines the temperature in the 4th power, is going to tell us that the temperature is going to be linear in the VEV. And so this is why we wanted the branching fraction to go as V to the 4th. It ensures that the temperature is linear in the VEV of each sector. So each sector is going to get a slightly different temperature. And the only thing that governs this is the Higgs VEV. And this is nice for us because the hydrogen binding energy is also linear in the Higgs VEV, since we fixed all the dimensionless constants to be the same in both sectors. The reduced mass essentially becomes the electron's mass. And so now the binding energy is going to be linear in the VEV. And so the ratios of the two sectors, B to T, are going to be the same as well. And that fixes the timing of recombination without any additional requirements. So this gets us most of the way there all by itself. Now, this decay also sets the baryon asymmetry in each sector. Now, once we've set up the potential for the Affleck-Dine field, we don't actually have to care very much about what its detailed properties are, because we know that it's an efficient mechanism of generating an asymmetry. What we just have to keep track of is what's the ratio of the baryon to entropy ratio that each sector gets. So that's governed by the branching fraction of phi to each sector, and it's governed by the entropy density of each sector, which is why we see G star S. This is the entropic degrees of freedom that each sector has activated for a given temperature. TRH is the reheat temperature that's established after the phi fields transferred its energy density to these two sectors. And so if we activate the same number of degrees of freedom in both sectors, then it's just a simple VEV ratio. So the asymmetries are not going to be the same in this story, which is kind of funny. But it turns out that that's going to be useful to us because this, in turn, ensures that the fluids have the same ratios. And so the way this works is, for example, if you look at this middle line of rho baryon to rho photon, we can write this in terms of eta, noting that the proton mass is approximately the same in both sectors. That ratio has the scaling of eta baryon proton mass divided by the reheat temperature. And you end up with the same scaling in the prime sector once you use the fact that eta is proportional to T reheat, which is proportional to the VEV. And so you end up with the same ratios of fluid components in the two sectors. As a bonus, you might recall that when we were looking at this pair of plots last time around, the fraction of atomic dark matter relative to the dark matter, the total dark matter, was a few percent 5% or so. And this was originally treated as a free parameter. Find the value of the fraction that gives a good fit to CMB observables for a given temperature ratio. But in this story, since we're creating both of these from the decay of a scalar field, that's not a free parameter in the story. And so you can just ask, what is the fraction of atomic dark matter relative to cold dark matter? And that also ends up being governed by this VEV ratio, which once you tell me that the VEV ratio needs to be 0.7, automatically returns about a 5% value. So this is automatically consistent with the kinds of relationships that we need to make sure that all of the ingredients are realized. It didn't have to work out that way. This is just a coincidence, but we're happy that it did. And having set this up, we have to ensure that certain criteria are satisfied. So at the end of the day, we would like to make sure that there's no, that the two sectors don't thermalize with each other. So if they were to thermalize, then that would spoil the temperature ratio and we'd be excluded from a variety of different directions. The only place where we've postulated an interaction that could potentially thermalize is through the interactions with phi, which are not negotiable. We have some parametric control over whether or not thermalization happens by setting the denominator scale of this higher dimension operator. This is morally the mass of some field that's been integrated out. And if we want to make sure that neither sector interacts with phi to an appreciable enough degree that it thermalizes with phi, then that should be sufficient to ensure that diagrams that have even more insertions of lambda that connect the two sectors to each other will not thermalize. And it turns out that as long as you're willing to satisfy this inequality, there shouldn't be any trouble. So lambda can be of modest size, make it a few TeV, make the reheat temperature something like 10 GeV, and we're all right. I should mention that we don't want the reheat temperature to go above the electroweak scale in either sector, because then that would make sure that would spoil the branching fractions of this field. Because once these operators are no longer represented in the electroweak vacua of the two sectors, then they're going to have a much more complicated dependence on other model parameters. Working in the broken vacuum ensures that all of the phi decays end up having the proportionality that we want. It gives the right amount to each sector. Which is actually what I just told you in leading up to this slide. We have to always be in the broken electroweak vacuum, and that imposes a certain requirement on the branching fractions and lifetimes of this field. Here, this is calculated on the assumption that the field dominates the energy density. So you map this on to whatever parameters govern the total width. We've checked that it isn't impossible to do this, that there are reasonable parameter choices that you can make given this construction. But at the end of the day, we do need to ensure that in both sectors, the reheat temperature is about, somewhere between an MeV and 100 GeV, which is not hard to realize, but it is sort of funny to think about a reheat temperature being maybe lighter than what we tend to intuitively imagine. Maybe it's 10 to the 6 or 10 to the 13 GeV. That's as high as it can go. We'd like it to be on the lower end. We also have to be careful in choosing the decay operator. So I'm not going to say too much about this, but what we generally need is something that enables us to write down an H² dependence. Here, H is the Higgs doublet, without allowing us to write down simpler operators. So one possibly intuitive choice for this would be that we add an additional BSM Dirac fermion. So this consists of two Weyl fermions, chi and chi conjugate. These are Dirac partners. They carry baryon number, but not lepton number. And the operator of standard model fields that also gives us the H² dependence can be something like the lepton doublet times the Higgs doublet, which is a gauge neutral object, and we square that. And then we finally give phi B minus L number so that its lepton number is saturated by the lepton doublet and its baryon number is saturated by chi squared. Notice that it's chi and not chi conjugate. And we might gauge B minus L in order to ensure that you couldn't just write down this operator all by itself. You would need to ensure that these things come in the right combination, the kind that we see here. And that puts this operator at fairly high dimension. We need a lambda to the 5th downstairs. And so what would happen in this version of the story is you set the Higgs at its VEV, then phi decays to the fermion and to leptons, and then it decays, then the fermion chi decays to 3 quarks through an additional operator that is consistent with all gauge and global symmetries that we care about. Because it's a Dirac fermion, we can decay it through its chi conjugate, even though the asymmetry is initially introduced in chi. And that puts the baryon and lepton numbers into the standard model. So what I'll leave you with is that.
Sorry, can I ask a question? Your
yeah.
Chi, what kind of mass do you have for chi?
There's not a strict requirement. As long as its decays take place before BBN, you're all right. So numbers in the tens of GeV are fine. You probably don't want it to be lighter than a GeV because you do want it to decay through the baryon portal here. But as long as it's promptly decaying relative to BBN, you're fine. As a summary, I'll tell you that dark atoms are interesting because if you add a mirror sector to the standard model that's not appreciably interacting with our sector, and it has an asymmetry and it undergoes the same sequence of cosmological transitions that our sector does, that's interesting because it realizes an approximate scaling symmetry of cosmological fluctuations, which might be an important ingredient in any realistic model that resolves the Hubble tension. To my knowledge, this is the only thing that will simultaneously give us a large value of H0 and actually give a good fit to CMB observables. And doing this requires what at face value might seem like some unlikely coincidences, but that if you tell a whole story involving Affleck-Dine baryogenesis, 2 non-interacting but otherwise similar hidden sectors whose asymmetries and energy densities and temperatures are just governed through one funnel, the decay widths of an Affleck-Dine scalar field in the early universe, then you can realize all of those ingredients. And that might have implications for other things as well that might be interesting. So you do have an asymmetry here, and you do have a weak force. And the weak force is a little bit stronger than it is in our sector because the Higgs VEV is a little smaller. And so maybe you could have appreciable nucleosynthesis. You might be able to form interesting structures like dark stars, dark nuclei, and so on. Maybe a double disk. This has been interesting in a number of contexts, but we didn't go into the details of any of that, although it might be interesting down the road. But ultimately, at the end of the day, we care about being consistent with observations. So the report card is, I would say we get reasonably good marks for having a mechanism that'll give the right kind of sector that's needed to provide a good fit to CMB data, but we still suffer the helium problem. And unfortunately, I haven't been able to tell you anything about how to resolve that. But if that could be overcome, I would be very excited to learn about how. So that's all I have prepared. And so I guess we can have some questions if people are interested.
Let's thank our speaker. I've been waiting to chat for a long time.
Great, thank you.
I think there's 2 questions, hands raised on Zoom. Why don't we start with those? Faye, do you want to go first?
Oh, sorry, that's not a raise hand, it's a claps.
Oh, I'm sorry. Okay, that was a clap. Thanks. Ian, did you have your hand up or was that a clap?
Also a clap.
Okay. Any other questions? I mean, I would like to just come back to the point I raised during the seminar. So I'm really pretty dubious that you can get lambda QCD to be unchanged to 1%. So let me ask you a question. Did you compute the 3 flavor lambda QCD that you get by integrating out the top, the bottom, and the charm?
Let me see. I was referring to a result in the literature. This was in the literature on twin Higgs cosmology, where this issue's come up before. Let me see if I can find the paper.
The reason I'm surprised is that the formula, just at one loop, looks something like, you know, if you have like a lambda QCD twiddle with some twiddled heavy quarks, it goes like lambda QCD twiddle is some power of MB twiddle over MB to some power that's order 1. And the same thing for all the other quarks, MC twiddle over MC, and you know, MB twiddle over MB, whatever, all 3. You're integrating out half the quarks. None of those numbers, none of those powers that appear there are suppressed. It just seems like it would be really amazing to me if you changed the ratio by 1/3, 0.7, whatever, right? And lambda QCD ended up being the same to 1%. Maybe there's some weird, I don't know. It just doesn't sound right to me. All these effects of all these quarks go in the same direction. There's no cancellation. There's no small numbers in this formula. I mean,
right. Well, okay. So one thing that I can point you to is equation 2.3 of the paper that I just put in the chat. And in fact, maybe I can just share my screen on that.
Well, it's okay. If you just, this may be a detailed question. I would just.
Well, no, but I think it's useful to look at it.
It just doesn't sound like that. Doesn't sound right.
So here's the formula that they gave us. So my recollection was that if you were to just take the expression that they've put here in 2.3, and then you would put in a ratio of say 0.7 into the VEVs that show up here, then I think it is at the percent level. But let me see if I can confirm that intuition. So I'm just gonna.
Oh, okay, that's okay. I mean, we're not going to settle this now. Maybe I'll think about it. It's just it's a little surprising.
My recollection is that if you set the Higgs VEV to 0, it would change the proton mass by 30% in the standard model. So that's sort of the ballpark.
30%. So okay. So then maybe, yeah. So then maybe a few percent is not totally. Okay. Look, I don't want to derail everything. It just seemed a little different from what I would have expected.
Yeah, I agree. It also went against my intuition on this, but if I just take the expression that's on the screen here and I set that ratio to be about 0.7, I get that the final lambda QCD ratio is about 0.97.
Okay.
So maybe there's a subtlety here that I'm missing, but it's worth looking at maybe more deeply.
Okay. Other questions?
What's the inflation scale?
Oh, I think it's actually compatible with just about any inflationary scale. It just sort of depends on how big of an asymmetry you want. It's degenerate with the other parameters that govern the size of the asymmetry from the Affleck-Dine potential, because ultimately you're sensitive to some product of scale factors, an inflationary scale, and to the coupling that violates the baryon number. And then you're also ultimately sensitive to when the particle decays. But we weren't terribly concerned with those details because usually the problem with Affleck-Dine is you get too big of an asymmetry. It's the only model that I'm aware of where you're not getting like 10 to the minus 10 generically, you're getting like order 1-ish asymmetries. And so usually what people need to do is they have like entropy dumps, or you make the parameters in the potential seem kind of suspiciously small. Like you have a kappa of like 10 to the minus 10 or something like that.
Okay.
But I don't think that plays a key role. You could probably choose any inflationary scale you want.
Okay.
And so the indirect couplings that exist, since they both both of these are coupled to this Affleck-Dine field. Those are small enough that there's just there'd be no signatures, you know, from any laboratory constraints, right? It's just unimpacted by.
So this is a good question. From laboratory constraints, almost by construction, no, because we have to satisfy the requirement that the two sectors don't thermalize with each other. And that in turn translates into a requirement on the coupling to the Affleck-Dine field. And so we want this field to be something that decays promptly enough to populate the universe in the way that we like, but is also weakly coupled enough to the point where it wouldn't allow for thermalization to take hold once that happens. So I don't think so. Maybe some of the other field that you would add to realize how the decay works can be accessible, like the chi field that I mentioned earlier.
Yeah, that one is, I would think that if you took the lambda in front of that thing to be of order of TeV, that's where you would start getting some sensitivity just from direct colliding. You know, we have up and down quarks in the protons that we collide at the LHC. And so that would just be a four-body interaction. And if you look at, you know, four-body interactions involving, say, quarks, they're typically constrained at the sort of 10 TeV level nowadays. This is some exotic thing, which, you know, decays. But anyway, that's the range where you would probably start having to think about it at least.
Yeah, absolutely. And in fact, there's a great paper on this topic from a few years ago by Jan Utswe and Brian Chouvet, where they're explicitly looking for displaced vertices at the LHC inspired by particles that have this baryon portal-like coupling. I mean, for the Affleck-Dine field itself, maybe you could imagine that if it's sufficiently light during inflation, you do need inflation to sort of kick it around and displace it from its minimum. So maybe there could be some sort of isocurvature handle on the fact that it's essentially a light degree of freedom, and the fact that although it's not required that its decay takes place in a matter-dominated phase, I would think the simplest versions of Affleck-Dine work with that as a starting point. And so you could imagine maybe that there's enhanced structure formation on small scales and things like that.
So what do you get for what do you get in the H0 Olympics?
It sort of depends on whether you're just going by goodness of fit to CMB data, where I think it works quite well. But then there's this YP issue. And so in that sense, I don't know. Because I mean, YP is not optional, right? We measure it in the late universe, and it sort of feeds back in as a consistency check for BBN calculations. And so, I mean, if someone were to maybe come up with a way to have it assume the usual value at BBN, and then somehow be reduced in a safe way during CMB, and then like repopulated to the normal value for late time observation, then we get the like platinum medal. But as that stands, this is why the word towards is in our title. We don't claim that we have a solution, but it's a way to think about the theoretical requirements needed to create sectors that would have a chance of maybe doing this if someone could solve this problem.
Yeah, I got the same question in a seminar recently, and I gave basically the same answer. It depends on how the referees of the H0 Olympics treat this helium problem, But then you compare to the competition, and they need an electron mass that's different than the electron, the gold medal winner. So anyway, that's.
Yeah, but let me ask you then, because my understanding of your analysis was that you allow YP to float so that you can enhance the electron photon scattering around the CMB era so as to tame silk damping. But did you think of any other alternative ways of doing that and just keeping YP fixed?
So one thing is that it's first, it's more than the silk damping. It's all the polarization gets generated then, right? And it's very dependent on that rate. So it's both getting the silk damping right and all the polarization spectra. And then and then as far as other ways to do it, I mean, one thing that I was excited about briefly was Cliff Burgess is working on some model for entirely different reasons, where there's some dilaton field that leads to all masses scaling relative to the Planck mass, and that things are kind of relaxed to their laboratory values through most of cosmological evolution, but there's some kind of tracking behavior that leads to departures around matter radiation equality, and so that you could get you could get the electron, all masses other than the Planck mass, and the electron mass changing relative to the electron mass changing, and so that would change the Thomson cross section. But the problem is that it would also change the binding energy of hydrogen. So that doesn't quite work. We'd also somehow need to change the fine structure constant too. Now, on the other hand, although not protected by the symmetry, phenomenologically, this varying electron mass without all this dark sectors hidden, without all this, the atomic dark matter, that phenomenologically works pretty well, and so. For reasons having nothing to do with this symmetry. So as far as so that's one potential way, and then another thing that we've been thinking about, just beginning to start thinking about, is some energy injection into the plasma. From some process that's some exotic process that's dumping energy into the plasma, and enough to slow down recombination, but not enough to create spectral distortions that we'd see in Phi-RAS. So that's another route towards increasing the number density of free electrons. But yeah, I mean, I think that actually trying to get the history of helium to work out is really hard, because you need, anyway, you described a complicated scenario, and then you'd also have to have BBN modified in a way that has helium coming out low, doesn't screw up deuterium to hydrogen, right? And then some early population of stars, I guess, to boost helium back up, just to get where you get the value of helium that you get from the standard model, right? I mean, it doesn't sound like a likely way to go.
Yeah.
Any other questions or comments?
Well, let's thank Gordan again, and anybody who would like can still hang out for a little bit, but let's thank him for a very nice seminar.